I will discuss De Morgan's theorem in the context of digital electronics, or to be more specific, in the context of digital logic gates. So it goes something like this. Let's say A and B are two variables. So A plus B invert can be written as A B. This is one form of De Morgan's theorem, and here what we observe is this one is can be implemented using a NOR gate, while this one is AND gates and two inverters. So basically this one will be, this side is like that, while this side will be two inverters. So A and B first inverted and then ANDed. So this is one form of De Morgan's theorem. The other one is A B bar is equal to A bar plus B bar. So basically similar, here it was OR and this one has become and the bar was on top of the whole thing. Here the bars are separated. Similarly here here is AND, the first one is AND the bar is on top of it, the top of the full expression, and this one is AND has become OR and bars are separately there. So this one is can be implemented using a NAND gate, while on this side this is again inverted first and then an OR gate. So like that. Now there is a very useful application of De Morgan's theorem for logic gate implementation. So let's say we have a sum of expression, sum of product expression AB plus CD. Now this one can be implemented using, if we want to implement this, if we have to use AND gates, two AND gates there for AB and CD, two AND gates, and then here it has to be ORed. So we have we have to use two type of gates. So two types are there. This is AND gate, it will require one IC, and this is an OR gate, this is another IC. Now what we can do using De Morgan's theorem, we can implement this expression using only one type of gate. So only one IC will be needed, and that's actually NAND gates. So what we can do here, A plus B plus C plus D, this one can be written as, we know that A can be written as A bar bar, invert, twice inverted. So similarly we will write this one first, CD, two bars. Now what we will do in this expression, here we will apply De Morgan's theorem. So I will write it again, this one, this one. Now the top above bar, the top bar remains there, but in this part we will apply De Morgan's theorem. So it will become AB bar dot CD bar, like that. So I have not changed the top bar, only the bottom bar I have changed, and now this expression has become, this is a NAND gate. So this one can be implemented, AB can be implemented here. This part is just AB NANDed, this part is CD NANDed, and then the whole thing is again NANDed. So there is another NAND gate, and we actually needed just 3 NAND gates to implement this whole expression, and it is one NAND gate IC, 14 pin IC will have actually, they contain 4 2 input NAND gates. So we can implement this whole expression using only one IC, one NAND gate IC. So this way it becomes simpler to implement if we apply De Morgan's theorem, and often this is what is done. So I will do another example later with a little bit bigger expression to show how sum of product expressions can be implemented using only NAND gates.